In this exercise, we are given a circle C and a point P. We are supposed to find a second circle that passes through P and that is orthogonal to circle C. First, we have to define what it means for two circles to be orthogonal. Let C' be a circle that intersects C and passes through P. Let O be the center of C and O' the center of C'. We say that circles C and C' are orthogonal if at each point of intersection the tangent to one circle at the point of intersection is perpendicular to the tangent to the other circle at the same point of intersection. Tangents to circles are also intimately related to their radii, that we can say that circles C and C' are orthogonal if the radius of one circle to a point of intersection is perpendicular to the radius of the other circle at the same point of intersection. We then have four cases to consider. For the first case, what if circle C' passes through the center O of circle C? These two circles should intersect at least one point different from O. The radius of C to this point of intersection is now a chord for circle C', and therefore cannot lie on the tangent line, tangent to C' at the point of intersection. So case 1 is impossible, unless we extend the definition of a circle to include lines that pass through the center of C. This way, at each point of intersection, the tangent line to the circle is perpendicular to the line through the center of the circle, and so the two curves are orthogonal. For case 2, suppose P is on C. We construct the radius to P and draw the tangent line to P. Apart from P, we can choose any point on this tangent line to be the center of C'. We leave it as an exercise for the viewer to show that there is orthogonality at the other point of intersection. For the third case, suppose P is outside C. We will construct the circle through P and that is orthogonal to C and justify orthogonality after the construction. First, we need to construct a circle different from the orthogonal circle. The circle that we first construct is the circle with diameter OP. Let M be the center of this circle. Suppose this circle intersects C at T1 and T2. Triangle OT1P is a right triangle, as is triangle OT2P. The reason we know this is that any triangle inscribed in a circle and that has one of its sides a diameter of the circle, as is the case of these two triangles, must be a right triangle. And so by the hypotenuse-like congruence for right triangles, these two triangles are congruent. Therefore, by CPCTC, otherwise known as corresponding parts of congruent triangles are congruent, the two angles at O must be congruent. The purpose of all these constructions right now is to locate a point called the inverse point of P with respect to C. Locating this inverse point is central to the construction of orthogonal circles. Segment T1, T2 intersects segment OP at a point we call P'. By side-angle-side congruence, or SAS congruence, triangle OT1P' is congruent to triangle OT2P'. And so invoking CPCTC again, we have nothing but right angles at P'. Now we examine a couple of right triangles. These are the little triangle OP'T1 and the big triangle OT1P. These two triangles are similar or proportional because they share the angle at O, and they are both right triangles. And so by AA similarity, these two triangles are similar. So we compare ratios between corresponding sides. Let R be the radius of circle C. We take the short side OP' of the small triangle and divide it by the hypotenuse R of the small triangle. We take the short side R of the big triangle and divide it by OP, the hypotenuse of the big triangle. And so OP prime divided by R equals R divided by OP, from which we get the product of OP prime and OP equals R squared. This is precisely the equation that defines what it means for the points P and P prime to be inverses with respect to the circle C. It is crucial to the construction of the orthogonal circle to circle C that we have the inverse point of P. We will see in a little bit that any conventional circle C prime, and that excludes lines, circles that pass through P will be orthogonal to C if and only if C prime passes through the inverse of P. We can easily find a circle right now that will be orthogonal to circle C. We use segment P, P prime as the diameter of this circle. We will prove that these two circles are orthogonal, but we will prove it for a more general situation. We take another point Q, any point Q on the plane, as long as Q is non-collinear with P and P prime. Any triangle, such as triangle P, P prime Q, can be inscribed in a unique circle. We just need to find the center of the circumscribing circle. To do this, we find the midpoint of each segment of the triangle. And then, through the midpoint of each segment, we construct the perpendicular to this segment. These perpendicular bisectors will intersect at the single point, called the circumcenter of the triangle. This is the center of the circumscribing circle. Let this circle be C prime and let its center be O prime. We claim that C prime is orthogonal to C. We will need a few more segments on the diagram to prove this claim. We will use segment P prime O prime and segment P O prime. We will also need the midpoint M of segment P P prime. Triangle P O prime P prime is isosceles because two of its sides happen to be the radius of C prime. Let R prime be the radius of C prime. Then segment OM is a perpendicular bisector of segment P P prime. The immediate plan now is to derive an equation involving segment O O prime. First, we let the length of segment OP prime be equal to A. Then we set the length of segment P prime M and segment PM equal to X. Let Y be the length of segment O prime M. Applying the Pythagorean theorem to triangle OMO prime, we get OO prime squared equals the square of the quantity A plus X plus Y squared. In order to prove orthogonality between the two circles, we need to express OO prime in terms of the radii of the two circles, and so we need to express X and Y in terms of R and R prime. We turn to the inverse point relationship between P and P prime. OP prime is equal to A, and OP is equal to A plus 2x. Therefore, OP prime times OP is equal to A times the quantity A plus 2x. So that R squared is also equal to A times A plus 2x. And we find that X is equal to R squared minus A squared, all over 2A. Next, we apply the Pythagorean theorem to triangle PMO prime. We find that Y squared is equal to R prime squared minus X squared. We replace X by R squared minus A squared over 2A and find that Y squared equals R prime squared minus the square of R squared minus A squared all over 2A. We go back to the equation involving OO prime squared and replace X and Y squared by what they are in terms of R, R prime, and A. OO prime squared is equal to the square of A plus R squared minus A squared all over 2A, which is the square of the quantity A plus X. To this we add Y squared, which is equal to R prime squared, minus the square of R squared minus A squared over 2A. This simplifies nicely into the Pythagorean equation OO prime squared equals R squared plus R prime squared. Because OO prime, R, and R prime satisfy the Pythagorean equation, OO prime, R, and R prime must be the sides of a right triangle, with OO prime as the hypotenuse. The two radii R and R prime are perpendicular at the points of intersection. Therefore, the two circles are orthogonal to each other. We have just shown that if P and P prime are inverse points with respect to circle C, neither of which is on C, then any circle C prime passing through P and P prime will be orthogonal to C. The converse is actually true. That is, if a point P is on C prime which is orthogonal to C, then its inverse point with respect to C will also be on C prime. We leave the proof of the converse as an exercise for the viewer. This brings us to the final case where P is inside circle C but is different from the center of C. Because of what we know about inverse points with respect to a circle C and circles orthogonal to C, all we need to do is locate the inverse point of P with respect to C. We construct line OP. We draw the line perpendicular to line OP at P. This line intersects C at 2 points that we call T1 and T2. We draw the radii to T1 and T2. Then we draw the line that is perpendicular to each radius at T1 and T2. These two lines intersect line OP at the inverse point P prime of P. All we have to do now is to find the center of a circle that passes through P and P prime. These centers happen to lie on the perpendicular bisector of the segment P, P prime. We leave this as the last exercise for the viewer.